This story starts not with a flash of light, but with a sound. It's the desperate cry of a newborn baby and the fear it strikes in the hearts of his parents. This is the story of KJ Muldoon. And before he even had a first birthday, he made medical history. He is the very first person to have his genes custom edited to correct a fatal flaw that was written into his DNA from birth. This isn't science fiction. It's the incredible true story of a breakthrough that shatters our understanding of what's possible. It's about a family's impossible choice, a team of scientists in a race against time, and a revolutionary technology that's opening the door to curing thousands of diseases we once thought were incurable. This is how science gave a child a future that just a few months ago seemed impossible. For Kyle and Nicole Muldoon, the first few days of their son KJ's life went from a blur of joy to an absolute nightmare. He was their beautiful newborn, but something was terribly wrong. Soon after he was born, he was diagnosed with a rare and catastrophic genetic disorder, carbamoyl phosphate synthetase 1 deficiency, or CPS1. It's a condition that affects maybe 1 in a million newborns. And for those children, the prognosis is devastating. More than half of babies born with severe CPS1 die within their first few weeks. Imagine your body has a waste management system that's essential for keeping you alive. Now imagine a critical piece of that system, a single enzyme in the liver, is just missing. For KJ, this meant his body couldn't break down protein. Every single time he was fed, a toxic substance called ammonia built up in his bloodstream, attacking his brain and organs. It's a relentless, invisible poison. As his father Kyle put it, when you search for CPS1 online, you find two phrases: fatality rate or liver transplant. That was the grim reality they were facing. A life of crisis management, just trying to keep their son alive long enough for a high-risk liver transplant, an operation that tiny infants are often too fragile to even survive. They were staring down an impossible choice with a countdown clock they couldn't see but could feel with every passing second. The Muldoon family's journey was whiplash. One moment they were celebrating a new life. The next they were in the sterile, beeping world of the Children's Hospital of Philadelphia, or CHOP, watching their son fight for his. CPS1 deficiency is a complicated name for a simple, brutal reality. The human body is a miracle of engineering run by a genetic code that's 3 billion letters long. In KJ's case, there was a single misspelling, just one faulty letter in one gene out of more than 20,000, and his entire system was failing. This one tiny error meant the CPS1 enzyme, which is crucial for the urea cycle in the liver, was completely absent. The urea cycle is the body's main detoxification pathway. It takes ammonia, a natural but toxic byproduct of breaking down protein, and converts it into harmless urea, which then gets flushed out of the body. Without that enzyme, it's like a city's entire garbage collection service going on strike forever. The trash, the ammonia, just keeps piling up. The levels in KJ's blood were dangerously high, putting him at constant risk of brain damage, seizures, coma, and death. The standard treatment for this condition is basically a desperate holding pattern. Doctors put these babies on a super restrictive, low-protein diet to minimize the ammonia. They give them drugs called nitrogen scavengers to try and grab the ammonia and pull it out of the blood. But these are just temporary fixes. They're a bridge to the only real long-term solution, a liver transplant. And this was the family's brutal dilemma. A liver transplant is a massive surgery for anyone, let alone a fragile infant. The waiting lists are long, the surgery is risky, and for the rest of their life, the recipient has to take powerful drugs to stop their body from rejecting the new organ. For a baby as small and as sick as KJ, he might not even survive long enough to be a candidate. Every single day was a balancing act. Every feeding was a risk. Even a common cold could trigger a catastrophic spike in his ammonia levels. Nicole and Kyle were living in a state of constant high alert vigilance, their lives governed by blood tests and monitors. With all their hopes pinned on a risky, distant solution, they were trapped. But what if you didn't have to replace the whole factory? What if instead you could just fix the one broken machine inside it? This question, once the stuff of science fiction, is now one of the most exciting frontiers in medicine, all thanks to a revolutionary technology called CRISPR. You've probably heard of it. It's the gene editing tool that's so groundbreaking its creators won the Nobel Prize. In simple terms, CRISPR works like a pair of molecular scissors. A guide molecule acts like a GPS, searching through the 3 billion letter library of the human genome to find one very specific spot, the faulty gene. Then an enzyme, most famously Cas9, swoops in and makes a precise cut in the DNA. That cut triggers the cell's own natural repair mechanisms. Sometimes the goal is to just shut off a bad gene. But in cases like KJ's, the goal was way more ambitious to actually correct the mistake. This is where a more advanced version of CRISPR called base editing comes in. Instead of cutting the DNA in half, a base editor works more like a pencil and an eraser. It chemically converts one DNA letter into another, directly fixing the typo. It's the difference between demolition and a meticulous, molecular-level renovation. For years, this technology has been moving from lab dishes to animal models, its potential growing with every discovery. The COVID effect also played a surprisingly crucial role. The mRNA vaccines used a delivery system called lipid nanoparticles, or LNPs, basically microscopic bubbles of fat that carry genetic instructions into our cells. Scientists realized this exact same system could be used to carry the CRISPR machinery into the body. At the Children's Hospital of Philadelphia, a team of researchers led by Dr. Rebecca Ahrens-Nicholas and Dr. Kiran Musunuru from the University of Pennsylvania had been working on this exact problem. When KJ arrived at their hospital, his devastating diagnosis collided with their cutting-edge research. His case presented a unique, high-stakes question. Could they do something that had never been done before? Could they build a personalized gene therapy for a single patient and do it fast enough to save his life? The moment KJ was diagnosed, the clock started ticking. The team at CHOP in Penn launched an unprecedented mission: create a custom cure from scratch. This wasn't a drug you pull off a shelf. This was a therapy designed, built, and administered for only one person on Earth. The entire process, which would normally take years, was squeezed into just a few months. First, they did a deep dive into KJ's DNA to pinpoint the exact misspelling in his CPS1 gene. That was their target. Next, they had to design the weapon. They created a unique guide RNA, the GPS, that would navigate KJ's entire genome and lock onto only that one faulty gene in his liver cells. They paired it with a specialized adenine base editor, ABE, the pencil and eraser that could chemically change the incorrect DNA letter A to the correct letter G, effectively rewriting the typo in his genetic code. Once they had the design, they tested it relentlessly in the lab on cells that had KJ's exact mutation. They had to be sure it worked, but more importantly, that it didn't create new problems. The fear of off-target effects, where CRISPR might accidentally edit the wrong part of the DNA, is a huge concern. So the team worked to make sure the therapy was incredibly precise. While all that was happening, another team was solving the delivery problem. They packaged the messenger RNA instructions for the base editor inside the lipid nanoparticles, LNPs. When these fatty spheres are infused into the bloodstream, they're naturally drawn to the liver, exactly where the repair needed to happen. With all the pieces designed and tested, the team presented their mountain of data to the U.S. Food and Drug Administration, FDA, to get permission for this single patient experimental treatment. Given the life or death urgency, the FDA gave them the green light through an investigational new drug pathway. In just a few months, they had gone from a diagnosis to a vial containing a potentially life-saving, personalized medicine. For Kyle and Nicole Muldoon, it was the ultimate leap of faith. They had to choose between the known danger of a liver transplant and the complete unknown of a medicine that had never been given to a human being before. In February of 2025, the moment arrived. KJ, now 7 months old, lay in his hospital bed at CHOP. His parents watched, caught between hope and terror. as the work of dozens of scientists condensed into a single IV bag was infused into his tiny arm. The lipid nanoparticles began their journey through his bloodstream, homing in on his liver, and then they waited. Did it work? There was no switch to flip, no immediate sign. All they could do was monitor his blood. For months, keeping his ammonia levels from spiking had been a constant, grueling battle. But then, something remarkable happened. Within weeks of that first infusion, the numbers started to drop, slowly at first, then more steadily. It was the first tangible proof that the microscopic renovation was working. The base editors were finding their target. They were rewriting the typo. His liver cells were starting to produce the enzyme they had been missing. The city's waste management system was slowly coming back online. Encouraged and with no serious side effects, the doctors gave him 2 more doses at 7 and 8 months old to correct even more liver cells. With each one, the positive signs grew stronger. And here's the real proof. His diet, for his entire life, protein had been poison. Now doctors gradually increased it until he was eating the normal amount for a baby his age, something that would have been a death sentence just weeks earlier. He even fought off a common cold without his ammonia levels going haywire. Everyone could finally breathe. It had worked. The change in KJ was astonishing. The frail, critically ill infant started to transform into a chubby, thriving baby. He gained weight. He started hitting developmental milestones. The small things most parents take for granted, a wave, a smile, rolling over, became monumental victories for the Muldoon family. After 307 days spent inside a hospital, baby KJ was finally cleared to go home. The videos show hospital staff lining the hallways, giving him a hero's clap out. A celebration not just for a patient going home, but for a pioneer who had just crossed a new medical frontier. For his family, the future was no longer something to dread, but something full of simple, beautiful possibilities. His mom, Nicole, said she was just looking forward to the little moments, like sitting on the couch on a rainy Sunday and watching a movie, all together. After so much uncertainty, the ordinary had become extraordinary. From a medical perspective, the success was profound. The therapy had corrected the genetic defect with no serious side effects. It meant KJ could eat, grow, and develop without the constant threat of toxic ammonia. Most importantly, it means he likely won't need a liver transplant. Science didn't just treat his symptoms, it fixed the problem at its very source. While he'll be monitored for the rest of his life, this breakthrough has given him a shot at a normal, healthy childhood. As Dr. Ahrens Nicholas, one of the lead physicians, said, "While KJ is just one patient, we hope he is the first of many to benefit." And that is the true meaning of this story. KJ's journey wasn't just about saving one life, it was about creating a blueprint. KJ's story marks a turning point. It's powerful proof that we now have the tools to develop and deploy personalized genetic cures for individuals. This moves us from the era of one-size-fits-all drugs to an age where treatments are tailored to a patient's own genetic code. This single success throws the door wide open for treating thousands of other rare genetic diseases, many of which have no cure at all. Conditions like cystic fibrosis, Huntington's disease, and muscular dystrophy. And the same platform used for KJ, combining advanced base editing with safe LNP delivery, can now be adapted to target different genes for different diseases. We are watching a new kind of medicine being born, one that corrects the fundamental cause of a disease instead of just managing the symptoms. And the pace of innovation is accelerating like crazy. New AI-powered tools are already helping scientists design these therapies faster than ever. And newer, more precise CRISPR systems are constantly being developed. Of course, big challenges are still ahead. The cost of these custom-made therapies is enormous, running into the millions of dollars per patient. Making sure everyone who needs them can get them will be a huge hurdle. And there are always complex ethical questions to consider as this technology gets even more powerful. But these are the challenges that come with progress. They're the problems you have to solve when a once impossible technology finally becomes a reality. KJ's story is just the beginning. We're witnessing the birth of a new kind of medicine written in the language of our own DNA. If you want to follow the breakthroughs that are changing our world, Make sure you subscribe and ring the bell for more stories from the frontiers of science. For decades, the promise of gene therapy felt like a distant dream. We always talked about its potential, but with KJ Muldoon, that dream became a reality. This wasn't a lab experiment. It was a real-world cure for a real child in need. It happened because of a family's courage, the dedication of a brilliant team of scientists, and the decades of research that came before them. We are entering an age where the word incurable might not be permanent anymore, an age where science can reach into our very cells and fix the typos that cause disease. The blueprint for a cure is no longer a fantasy. It's being written one genetic letter at a time.